So, we talk a lot about the tech that's in your pocket, on your desk, or in your living room right now, the latest flagship phone, the thinnest laptop, the smartest headphones. But every so often, it's worth taking a step back and looking out towards the horizon. What are the fundamental shifts, the groundbreaking innovations brewing in labs right now? These are the building blocks of the next decade. Some of it might sound like science fiction, but the groundwork is being laid today. This is the stuff that will reshape industries, societies, and our daily lives. So, grab a drink, get comfortable, and let's get into it. Artificial intelligence has quietly shaped our world for decades, powering recommendations, filtering spam, and automating tasks behind the scenes. But now, AI is evolving from a hidden tool to a creative partner, writing code, generating art, and collaborating with us in ways once thought impossible. This new era means smarter assistants, more creativity, and a future where AI amplifies what it means to be human. So, if AI is about rewriting the rules of what computers can do, our next topic, quantum computing, is about rewriting the very rules of computing itself. To understand why this is such a big deal, you have to think about how your current computer works. Whether it's a phone or a supercomputer, it's all based on bits. A bit is a simple switch. It can either be a 0 or a 1, on or off. All the incredible things our devices do are just the result of manipulating billions of these simple on or off switches incredibly fast. It's a powerful system, but it has fundamental limits. Quantum computers throw that entire binary concept out the window. Instead of bits, they use what are called qubits, and this is where things get a little mind-bending. Thanks to a quantum mechanical principle called superposition, a qubit can be a 0, a 1, or both at the same time. It exists in a probabilistic state, a spectrum of possibilities. It's like a spinning coin, whereas a classical bit is a coin that has already landed on heads or tails. This ability to exist in multiple states at once is what gives quantum computers their almost unbelievable processing power. And it gets even weirder. There's another principle called entanglement, which Einstein famously called spooky action at a distance. When two qubits are entangled, their fates are linked, no matter how far apart they are. If you measure one and find it's a 0, you instantly know the other one is a 1, and vice versa. By linking qubits together through superposition and entanglement, a quantum computer can explore a vast number of potential solutions to a problem simultaneously. While a classical computer has to check each possibility one by one, a quantum computer can look at them all at once. This doesn't mean your next iPhone will be a quantum computer. For many tasks, like browsing the web or sending an email, your classical computer is actually much better and more efficient. Where quantum computers excel is in solving a specific type of problem, complex optimization and simulation problems with an astronomical number of variables. These are problems that are so complex that even the most powerful supercomputers on Earth today would take millions of years to solve. For a quantum computer, it could be a matter of minutes or hours. It's a specialized tool for impossible problems. We've seen AI and quantum computing push boundaries, but to unlock their full potential, we need a network that's just as advanced. That's where 6G comes in. 6G isn't just about speed, it's about connecting everything, everywhere, intelligently. Imagine microsecond latency, terabit speeds, and a network that senses and adapts to our world. This is the foundation for the truly futuristic applications we're about to explore. So, you have this incredibly fast, low-latency network. What do you do with it? One of the biggest beneficiaries will be extended reality, or XR. This includes virtual reality, augmented reality, and mixed reality. VR immerses you in a digital world, AR overlays digital info onto the real world, and MR blends both, making digital objects interact with the physical world. The future of XR relies on 6G and edge computing for seamless, real-time experiences. So we have intelligent AI, a lightning-fast network, and new ways to interact with digital information. When you combine all of these, you get the engine for the next industrial revolution, hyper-automation. This isn't just the simple automation we've seen for decades, like a robotic arm on an assembly line doing one repetitive task over and over. Hyper-automation is about using a combination of technologies, AI, machine learning, robotics, and sophisticated sensors, to automate complex end-to-end business processes. It's about creating systems that can not only perform tasks, but also discover, analyze, and improve the processes themselves. It's automation that learns and adapts. Think of it as giving a business a digital nervous system. In a modern factory, for example, it's not just about robots assembling products. It's about an integrated system where AI analyzes supply chain data to predict component shortages, adjusts the production schedule in real time, and uses computer vision to inspect every single product for defects with superhuman accuracy. If a machine on the line starts to show signs of wear, the system can predict a potential failure and schedule maintenance before it ever breaks down, preventing costly downtime. This level of orchestration and intelligence goes far beyond traditional automation. This integration of robotics, AI, and sensors is what leads to truly autonomous systems. We're talking about more than just a self-driving car. Imagine a massive logistics warehouse where fleets of autonomous robots manage everything from unloading trucks to sorting packages to picking and packing individual orders. These robots don't just follow pre-programmed paths. They communicate with each other and with a central AI to dynamically optimize their routes, avoid collisions, and work collaboratively to fulfill orders with incredible speed and efficiency. Amazon is already doing a version of this, but hyper-automation will take it to a whole new level of sophistication and autonomy. The same principles apply to other industries as well. In agriculture, autonomous drones and tractors equipped with advanced sensors can monitor crop health on a plant-by-plant basis. They can apply the precise amount of water, fertilizer, or pesticide exactly where it's needed, dramatically increasing yields while reducing environmental impact. This is often called precision agriculture. In construction, autonomous bulldozers and cranes could work around the clock, guided by digital blueprints, to build structures faster and more safely than ever before. The core idea is to automate not just the physical labor, but also the decision-making and optimization that surrounds it. Let's dive into something more biological: DNA, the code of life itself. With tools like CRISPR, we're not just reading DNA, we're editing it. Imagine curing genetic diseases at their source, or programming cells to create new medicines and materials. Synthetic biology is transforming life into a platform for innovation, reshaping health, sustainability, and the future itself. What if the structure of a car, a phone, or even a building could also be its battery? Structural battery composites combine strength and energy storage, letting the body itself power the device. Imagine electric cars, drones, and electronics that are lighter, more efficient, and have longer range, because their frames store energy. It's a game changer for design, efficiency, and the future of technology. When we think of clean energy, solar and wind come to mind, but there's a massive untapped source: osmotic, or blue, energy. It's the energy released when fresh water meets salt water, happening naturally at river mouths worldwide. Using special membranes, this process creates pressure that can spin turbines and generate clean, reliable electricity. The global potential is enormous, enough to power entire cities. Material science is making this future possible. So let's talk about something incredibly small that has the potential for some seriously huge impact. I'm talking about nanotechnology, and specifically, a class of materials called nanozymes. Now, the name itself is pretty descriptive: nano for nanoscale, and zyme like enzyme. These are synthetic, man-made nanomaterials that are engineered to mimic the function of natural enzymes. Think of enzymes as the biological catalysts that speed up chemical reactions in our bodies, making life possible. They're super efficient, super specific, but they can also be fragile and expensive to produce. So what if we could build something better? That's where nanozymes come in. Engineers are creating these tiny particles, often from materials like iron oxide, gold, or carbon nanotubes, that can do the same job as enzymes, but with some key upgrades. They're more robust, meaning they can withstand harsher temperatures and pH levels where natural enzymes would just break down and stop working. They're also cheaper to produce at scale, which is a massive deal when you're talking about widespread application. It's like taking a high-performance but very finicky biological machine and reverse engineering a more durable, mass-producible version. It's a materials science win, honestly. The level of control here is just wild. By tweaking the size, shape, and surface chemistry of these nanoparticles, scientists can fine-tune their catalytic activity. They can make them more or less reactive, or even target specific molecules. It's like having a full soundboard to mix the perfect chemical reaction, instead of just a single volume knob. This precision opens up a whole new playbook for applications. We're not just copying nature, we're building upon its principles to create tools that are custom designed for the specific problems we need to solve, whether that's inside the human body or out in the environment. And this isn't just a lab curiosity anymore. We're seeing nanozymes being developed for everything from biosensors that can detect diseases with incredible sensitivity to therapeutic agents that can target and destroy cancer cells. The core idea is simple: build a better, stronger, cheaper catalyst. But the implications are profound. It represents a fundamental shift in how we approach biochemistry, moving from harnessing nature to actively designing and engineering its core components from the ground up. The sheer potential packed into these microscopic particles is, frankly, mind-boggling. Okay, so we've all heard of the Internet of Things, or IoT. You know, your smart thermostat, your connected doorbell, maybe your fridge. But the next evolution of this is something much more powerful: collaborative sensing and distributed intelligence. This isn't just about individual devices reporting data back to a central cloud server anymore. We're talking about a massive, decentralized network of sensors that can communicate and collaborate with each other directly, making decisions in real time without a central bottleneck. It's like giving the environment itself a nervous system. Think about it. Instead of one camera on a street corner, you have hundreds of sensors. Cameras, microphones, temperature sensors, air quality monitors, LiDAR on autonomous cars, all sharing data with each other. This is what we call a sensor fusion. No single sensor has the full picture, but by combining or fusing their individual data streams, the network can build a rich, detailed, and incredibly accurate model of the real world as it exists in that exact moment. It's the difference between looking through a keyhole and having a full 360-degree panoramic view of the room. This collaborative aspect is key. A sensor on a traffic light could detect an approaching ambulance and communicate that information to all the other traffic lights and connected cars in the vicinity. The system could then automatically turn all the lights green along the ambulance's path, clearing a route instantly. This isn't a person in a control room making a decision. It's the network itself sensing, collaborating, and acting autonomously. The intelligence is distributed across the entire system, not centralized in one place. This creates a system that is not only faster, but also way more resilient. If one sensor, or even a group of sensors, goes offline, the rest of the network can adapt and fill in the gaps. There's no single point of failure. This distributed model, where processing and decision-making happen at the edge of the network, close to where the data is collected, is what makes this real-time collaboration possible. It's a fundamental architectural shift, from a simple hub-and-spoke model to a true, interconnected web of intelligence. Alright, for years, the narrative in tech has been all about the cloud. Send your data to a massive, powerful server farm, let it do the heavy lifting, and get the result back. But there's a newish paradigm that's flipping that script, or at least complementing it in a huge way. Edge computing. The core idea is simple and elegant. Instead of sending all your data on a long round trip to the cloud, why not process it right where it's created? Right there on the edge of the network, on the device itself, or on a small local server nearby. This solves one of the biggest bottlenecks of the cloud latency. That's the time delay it takes for data to travel to the server and for a response to come back. For a lot of things like watching a video, a little bit of latency is fine. But for something like an autonomous car that needs to decide whether to brake in a fraction of a second, Sending data to the cloud and waiting for instructions is just not an option. It's way too slow. Edge computing allows that car to process its sensor data, from its cameras, its LiDAR, its radar, instantly, right on its own onboard computers. Beyond speed, there's the issue of bandwidth. Think about a factory floor with thousands of high-resolution cameras doing quality control. Streaming all that video data to the cloud 24/7 would be incredibly expensive and would clog up the network. With edge computing, you can have a small server on site that processes that video locally. It only sends the important stuff to the cloud, like alert defect detected on part number 74B. This drastically reduces the amount of data you need to transmit, saving a ton of money and network resources. And then there's the big one, privacy and security. Every time you send your data to the cloud, you're creating a potential point of vulnerability. It could be intercepted in transit or compromised on the server. By processing sensitive information locally, on your phone for example, that data never has to leave your device. Think about biometric data like your face or your fingerprint. On-device intelligence means your phone can authenticate you without ever sending that personal data over the internet. It's a fundamentally more private and secure architecture. Money has always meant coins, notes, and digital numbers in banks, centralized and based on trust in institutions. But what if we could build a financial system on a different foundation? That's the core idea behind decentralized finance, or DeFi, using blockchain to create a transparent, secure, and open financial system, run by code, not middlemen. With smart contracts, anyone can access automated financial services, no bank manager required. Okay, so we've talked about a lot of individual technologies, AI, advanced materials, biology, but what happens when you stop looking at them in silos and start smashing them together? That's where you get to bioconvergence, and honestly, this might be one of the most mind-bending shifts on the entire list. This isn't just about using a computer to analyze biological data. This is about the deep, fundamental integration of biology with digital and physical systems. We're talking about engineering living cells, like they're tiny computers, and building materials that can grow, heal, and adapt like living organisms. It's a true mashup of disciplines. At its core, bioconvergence is about treating biology as a programmable platform. For decades, our approach to biology was observational. We studied it, tried to understand it, and intervened with relatively blunt tools. Now, thanks to breakthroughs in gene editing like CRISPR and our ability to generate and analyze massive biological datasets with AI, we're moving into an engineering phase. We can read, write, and edit DNA with unprecedented precision. This allows us to program cells to perform new functions, like producing specific proteins, detecting diseases, or even creating novel materials. It's a paradigm shift from discovery to design. Let's look at materials science for a second. Traditionally, we manufacture things by taking raw materials and processing them, often using a lot of heat, pressure, and harsh chemicals. It's a top-down approach. Bioconvergence flips that script. It enables a bottom-up approach, using biology's own manufacturing processes. We can engineer yeast or bacteria to produce everything from spider silk, one of the strongest materials known to man, to bioplastics that are fully biodegradable. Imagine buildings with walls made of material that can heal cracks on its own, or clothes made from fabric that was literally grown in a vat, perfectly tailored to your needs. This convergence also creates a powerful feedback loop. We use digital tools like AI and machine learning to design new biological systems. Then, those biological systems can act as sensors, gathering data from the real world. Think bio-wearables that monitor your blood chemistry in real time. That data is then fed back into our digital models, which learn and refine their designs. It's a closed-loop system where the digital, physical, and biological worlds are constantly informing and improving each other. This is how we get to things like living pharmacies, implantable devices with engineered cells that monitor for a disease marker and automatically produce and release the exact dose of medicine needed. Alright, so we all know the big players in green tech: solar panels, wind turbines, electric cars. And those are incredibly important, no question. They're doing the heavy lifting for decarbonizing electricity and personal transport. But what about the rest of the economy? I'm talking about the really hard-to-abate sectors, like heavy industry, agriculture, and shipping. These are responsible for a massive chunk of global emissions, and you can't just stick a battery on a cargo ship or a solar panel on a cement kiln and call it a day. This is where the next wave of sustainable innovation comes in, focusing on deep, systemic solutions. One of the biggest and least talked about challenges is ammonia. We use massive amounts of it, primarily to make fertilizer that feeds the planet. But the way we make it, the Haber-Bosch process, is incredibly energy-intensive. It consumes something like 1 to 2% of the entire world's energy supply, and is responsible for a huge amount of CO2 emissions. So, finding a cleaner way to make ammonia is a massive lever for decarbonization. This is where green nitrogen fixation comes in. It's about developing new electrochemical or biological processes that can create ammonia at room temperature and pressure, using renewable electricity. If we can crack the code on green ammonia, the impact is twofold. First, we dramatically clean up the agricultural sector. We could have distributed on-farm ammonia production powered by local solar or wind, eliminating the emissions from both the production process and the transportation of fertilizer. This makes food production more sustainable and resilient. But the second part is even bigger. Green ammonia is also a fantastic energy carrier. It's a stable, dense liquid that can be burned in an engine or used in a fuel cell, releasing only nitrogen and water. It could be the clean fuel that powers the global shipping fleet. This is just one example of a broader trend in green tech, moving beyond just electrons to molecules. We're getting good at making clean electricity, but many industrial processes need chemical feedstocks and high-temperature heat, not just electricity. The next frontier is Power to X, where we use clean electricity to create green hydrogen, green ammonia, or synthetic fuels. These green molecules can then be used to decarbonize steel manufacturing, create sustainable aviation fuels, and provide long-duration energy storage. It's about building a circular carbon economy, where we use renewable energy to recycle CO2 into valuable products. Quantum computing promises incredible power, but our current networks can't keep up. Enter the quantum internet, a network built on quantum mechanics, where data is secured by the laws of physics. Quantum key distribution sends encryption keys as photons. If anyone tries to intercept them, the key is instantly corrupted. This makes data transmission fundamentally unhackable, a true paradigm shift in security. AI has mastered digital tasks, writing code, creating art, even beating chess grandmasters. But most AI still lives in server racks, experiencing the world through data. The next leap is embodied AI, robots that perceive, reason, and act in the real world. With advances in sensors, hardware, and edge computing, these robots are moving from labs to warehouses, factories, and beyond. Generative AI is transforming content creation. From stunning images and music to emails and code, AI now creates original work, not just analyzes data. Anyone with a web browser can generate art, write, or compose music. No special skills needed. This democratizes creativity, making powerful tools accessible to everyone. For years, building software was only for those who could code, or those who could hire them. But now, thanks to AI and no-code platforms, anyone can create apps visually, like building with digital Legos. Drag, drop, and connect. No need to write code or configure servers. Now, business owners and professionals can build custom solutions fast, accelerating innovation for everyone. So, let's talk about something that's been in the background of the energy conversation for a while, but is now getting a major spec bump: nuclear power. For decades, when you heard nuclear, you probably thought of these massive, sprawling power plants, super complex and honestly a little intimidating. The build times were epic, the costs were astronomical, and the public perception, well, it's been mixed, to say the least. But what if we could take that core concept, splitting atoms to generate immense carbon-free energy, and completely re-engineer the user experience? That's the core idea behind the next generation of nuclear tech. We're moving from a monolithic, one-size-fits-all design to something much more modular, flexible, and, dare I say, approachable. The key innovation here is the Small Modular Reactor, or SMR. Think of it like this. Instead of building one giant, custom-built mainframe computer, you're now deploying a series of powerful, standardized, server-sized units. These SMRs are designed to be manufactured in a factory setting, like you would assemble a car or a smartphone. This completely changes the economics and the timeline. It's about bringing economies of scale and quality control to an industry that has traditionally been defined by bespoke, one-off mega projects. The design philosophy behind these new reactors is also a huge leap forward. We're talking about a fundamental shift towards passive safety systems. In older designs, safety often relied on active systems, pumps, generators, and human intervention that needed to work perfectly in an emergency. The new approach is to use the laws of physics itself to keep things safe. Think gravity-fed cooling systems or materials that inherently shut down the reaction if temperatures get too high. It's like designing a phone that automatically throttles its performance to prevent overheating, but for a nuclear reactor. This makes them not just safer, but simpler to operate. This shift has massive implications for where and how we can use nuclear power. The sheer size and water requirements of old plants limited them to very specific locations. SMRs, on the other hand, can be deployed in a much wider range of environments. They could power a remote industrial complex, a data center cluster, or even a small city, providing a stable, 24/7 power source that doesn't depend on whether the sun is shining or the wind is blowing. It's about decentralizing a power source that was once the definition of centralization, and that opens up a whole new playbook for building a clean energy grid. Okay, let's switch gears from macro-level energy grids to the most personal tech imaginable, the technology of you. For years, we've been tracking our health with smartwatches and fitness bands, counting steps, monitoring heart rate, and tracking sleep. It's been cool, it's been useful, but it's really just been scratching the surface. We're now entering an era of integrated health and biosensing that goes so much deeper. We're talking about moving from simple activity tracking to continuous, real-time monitoring of our core biology. It's about turning the human body into a rich, high-fidelity data source. The hardware is evolving at an incredible pace. We're seeing wearables that are less like clunky gadgets and more like seamless extensions of our bodies. Think ultra-thin, flexible electronic tattoos that can monitor vital signs without you even feeling them. Or smart contact lenses that can measure glucose levels in your tears. The goal is to make the sensor invisible, to make the data collection ambient and continuous. This constant stream of information provides a baseline of your personal health that is incredibly detailed, allowing for the detection of subtle changes that could signal the onset of an issue long before you'd ever feel a symptom. This constant data stream is the foundation for a truly personalized approach to medicine. Your doctor's visit of the future might not start with you describing your symptoms. It might start with them analyzing weeks or months of your continuous biosignal data. They could see the exact moment your sleep patterns were disrupted, or when a subtle arrhythmia first appeared in your heart rhythm. This allows for a shift from reactive healthcare, treating sickness when it happens, to proactive and predictive healthcare, intervening before a condition becomes serious. It's the difference between getting a low battery warning and your device just shutting down unexpectedly. And it's not just about detecting problems. This level of integrated sensing can optimize performance and well-being in a way we've never been able to before. Imagine a system that analyzes your brainwave activity via a discrete headband and suggests the perfect time to take a break for maximum productivity, or a biosensor that monitors your hydration and metabolism in real time during a workout, giving you precise guidance on what to drink and when. This is about using data from your own body to make better decisions every single day, creating a feedback loop for a healthier life. It's the ultimate personalized user manual. So, we've covered a lot, from re-engineering the atom for clean energy, to turning our own bodies into real-time data streams, to the very frontier of brain-computer interfaces. It's clear that the future isn't being shaped by just one single breakthrough. It's a convergence of all these different fields: AI, biotech, material science, quantum physics. Each one is a powerful technology in its own right, but their true impact comes from how they connect and build on each other. An AI is more powerful running on a quantum computer. A biosensor is more useful when its data is processed at the edge. It's a portfolio of innovation. These technologies are more than just cool gadgets or abstract scientific concepts. They are the fundamental building blocks of the world our kids and grandkids will live in. They're going to redefine everything from how we cure disease, to how we power our cities, to what it even means to be human and interact with the digital world. The pace of change is accelerating, and staying informed about where we're heading has never been more important. This isn't about predicting the future with perfect accuracy, but about understanding the trajectories, the possibilities, and the important questions we need to be asking along the way. And that's really what we try to do here. We break down the tech, look at the hardware, analyze the impact, and start the conversation. The future is being built right now, in labs and startups and research institutions all over the world. And it's one of the most exciting stories unfolding. If you want to keep up with that story and get a closer look at the tech that's shaping our tomorrow, definitely think about hitting that subscribe button and turning on notifications so you don't miss what's next. We've got a lot more to dive into, but for now, I want to hear from you. Out of all the technologies we've talked about in this series, which one do you think will have the single biggest impact on our lives in the next decade or two? Is it the creative explosion of generative AI? The medical revolution from CRISPR and biosensors? Or the fundamental shift in computing from quantum? There's no wrong answer here. Drop your thoughts in the comments below. Let's get the discussion going. It's been Marcus.